2022-23 in the electrical engineering discipline. There are many more awards and disciplines with the name of Professor Arnagos. By this, I would like to call Professor Arnagos to deliver your talk, sir. Thank you, sir.
Thank you. Thank you. Is my screen is visible? Am I audible properly?
You're visible, sir.
Okay. Am I audible properly?
Yes, sir.
Okay. So very good morning, all the esteemed participants. I'm Arno going to deliver my presentations on intelligent power management scheme for microgrid applications. Basically, before starting the sessions, we need to know about the motivations of that presentation. Basically, what is the meaning by that microgrid? So one by one I am coming. So okay, so this is a miniature versions of that micro normal grid. Okay, so before coming that microgrid, so first we need to know about why that power management is important and why the intelligent power management is applicable for the applications. So first the motivations of the lecture. Okay, so I've already told you that microgrid means it's a miniature version of that grid. Suppose like that in power system when we have started. So basically we have designed that generating station nearer to our base load. Okay, so generating stations are designed nearer to the base load. Okay, in that case the problem was that it was a standalone system. So suppose anyhow any in the conventional grade actually, so if there is a absence of a fuel, so we cannot generate the power from that source. After that the grid concept has a bus concept has came. Okay, so for any kind of situation, so the power can be coming from one one end of our country to another end based on the requirement. Okay, now if the renewable has came to the picture, basically like that the adverse effect of the fossil fuels. Okay, so as well as the scarcity of the fossil fuels with the coming within the coming decade. So we have to generate, we have to develop the system of that alternate source of energy. Okay, so that's why the renewables are the good options for these applications. Okay, but the main problem is that if you are having a system with multiple renewable sources, so what you need to do? In that case, we have to design the power management. Suppose we can take an example. So if you are having a renewable grid, renewable microgrid with having a different source like solar photovoltaic, wind, okay, as well as sometimes hydel, okay, so as well as the storage systems. Okay, so if all the components are working simultaneously or all the components are working in which dimensions, means priority basis, okay, that normally decided by the power management scheme. Okay, so why the intelligent terms has came? Intelligent terms means like that all the renewables mostly are that intermittent in nature. Okay, so the what is the meaning of the intermittency? You can say like that day by day. You don't know when the based on the wind speed, based on the availability of the solar. Evening time the solar is not available, but wind can be available. So the intermittency nature. Okay, so who will decide the controllers to operate which renewables and which time? That will be coming for the intelligent deciding factor of the controllers. Okay, especially the power management algorithms. Okay, that's the motivations and that's the idea for the intelligent power management scheme for the microgrid applications. So it's an informative lecture. Okay, as well as we are having some of the results where we can able to see some idea how it is operating, how it is working on some hybrid microgrid. Okay, so before starting all those things, we are having some basic slides. So we have started from the crash level. Okay, how the converters are designed. Okay, so how the converters are involved with the system. Okay, so everything we are going to discuss gradually, and finally we'll decide some of the results. So from there we can able to understand how the actual system can work with that process. Okay, so this is the basic idea of that introductory part of our lecture. So basically that why renewables are very much important. So our government has taken oath in the Paris Agreement. Okay, so by 2030, 2 degree of 2 degree of temperature, environmental temperature will be reduced. For that one, government has taken national action plan for the climate change. So they have given focus on some of the aspects. Suppose conservations of our natural resources like river, forest, okay, means any kind of natural resources, water, okay. Next thing is that like that we can able to focus on some renewable based applications from and the sustainable transportation, renewable applications and the sustainable transportation. From there we can able to reduce the carbon footprint, so that can be that cannot generate adverse effect to our environments. Okay, now the applications point of view means utilizations point of view. So we can able to see the entire power system generation point of view, then the transmission point of view, and the applications point of view. So as we are talking about some captive generations, like your system design based on that your system design based on that your base load. So the generating stations will be based on the renewables and the utilizations. Basically, we can say like that utilization means how efficiently you are utilizing the energy. Okay, without creating any kind of losses. So utilization factor is very much important. So in this case, what happened? You can take an example just like an illuminations kind of load. So early days, what happened? We are using some halide lamps. Its rating was very much high. Okay, so more than 500 watt. After that, the fluorescent lamp we are also using. Their rating also 200 watt, 100 watt. Now the like that. Sorry, tungsten filament lamp. It was your rating was 100 watt, 200 watt. After that, the fluorescent lamp has came. Its rating also quite reduced. It is 40 watt. Nowadays, where after that our next generation, the CFL has came. Okay, so their rating also becoming in the range of 20 to 25 watts. Depends. Finally, we are using that LED lamps. So for our common purpose. So their rating on average, so we are using the 9 watt. Why 9 watt? Government is giving subsidy on the 9 watt lamps. Okay. So like that one. So main purpose is the illumination, but the rating of the system has gradually decreased. Okay, so basically the utilization is improved. We can reduce the losses. Here we can able to see the pollution index. So our different cities of our country is quite ahead for the neighbor countries. Okay, so that's why the renewables is that only options for that one. So now we are giving some brief idea about the microgrid. So it's a very common thing. So I hope most of the person are aware about it. Still, I have given some of the basic idea on that. Okay, so here we can able to see like that in the microgrids we are talking about different sources. Okay, so sources means we are having different renewable sources like solar, photovoltaic, wind. Okay, these are the sources, as well as we are for the microgrid, as we are told that it's an if we are depending on the renewables, so intermittency is the common term. That's why you should have a strong storage system. Okay, it can be the battery storage or it can be the hybrid storage. Okay, so that can be used for the backup or maintaining the reliability of the system. Okay, and like that in the case of load, so what type of load you can able to see here? You can see different buildings. Okay, so building management system, that power as well as the EV. So these kind of loads are also there. Okay, so these are the basic components for the microgrids. Okay, so it's a miniature version of the grid. Okay, and like that sometimes it can be operated in the two modes, standalone mode as well as islanded conditions. Okay, sorry, islanded conditions and the or the standalone mode or the grid connected mode. Okay, grid connected mode means it is your conventional grid, so that can directly connected with your microgrid based on the operations of the circuit breaker. Okay, so if all the system has failed, so for maintaining the continuous power supply to your load, so you have to connect the microgrid to the system. And who is taking care about the entire process? So definitely there is some control systems. Okay, so we know that different control systems are applied like that, you know, IoT based, okay, so Internet of Things based. Now we are using some advisory controls, okay, coordination control. So all are the different DG, distributed generation. So in between the coordinations happen. So in the control aspects means the reliable things will be there. They can controlling the how much, what is the projected way of power transferring, what are the operations, everything will be maintained by the control system. So here you can able to see some radial. Okay, so here you can see some that one. So residential, what are the different types of load? Residential, commercial, industrial. So generator is there, renewables are there, and the storage. Okay, electric vehicle is a multi-purpose, means it can be used as a load as well as sometimes the storage of the vehicle can also provide the energy to the local microgrid. So the controller basically is there that can be having three components. One is one can be the monitor, so it can monitoring the system. Another thing is that it's the controlling the system, and for the whatever controllers are there that can be controlled. Okay, and finally the balancing means stability. Okay, so is any kind of disturbance has came, so how the stability can be maintained. And finally the utility grid will be there, so if it is required, so utility grid directly connected to the system, connected to the microgrids, and it can be operated. Okay, this is the basic structure of the microgrids. Now the some definitions are there. I hope these definitions are very common to all of us, so I am not going to again repeat all those things. So we have already discussed about the microgrids. Okay, so microgrids are main thrust of work over there. So here we are having a slide based on the classifications. Okay, so classifications of the microgrid. So microgrid can be classified in different aspects based on their operations. Okay, based on their types, source of the based on the source, scenario of the applications, and finally the rating of the size of the microgrid. So here we are able to see already discussed that what are the types. So first thing is that based on the mode of operation, it can be worked like a isolated or islanded. Okay, islanded mode of operations or grid connected mode of operation. Two modes of operations are important. For these discussions, we are giving more trust on that only the isolated microgrids. Okay, how the stability can be maintained with the isolated microgrids. Then the types of the microgrids. Okay, there are three types of microgrid. Okay, AC microgrid, it can be DC microgrid, and hybrid microgrid. So in these discussions, we are giving trust on the DC microgrid, and after that we are talking about the hybrid microgrids. So means both AC DC both are there. Okay. Based on the source, it can be renewable in microgrid, diesel generator based means conventional based, and the hybrid. Hybrid means both conventional and fossil fuel based microgrid as well as the renewables. Both are present in the hybrid. So for the renewables, so it can be the solar photovoltaic based, wind, small hydro, the pico hydro, biomass gasifier, and hybrid means all source can be present. So if the power management will be required, so all source must be present over there. And the scenario based means what are the types of load. So it can be used like the residential load, industrial load, and the commercializations of your load. And the rating, based on the rating, it can be the less than 10 kilowatt, okay, and 10 to 1 megawatt, and more than 1 megawatt. So these are the very basic classification of the microgrids. Here we will start about the DC microgrid. In case of DC microgrid, whatever sources you have, you are converting the outcomes of the source, okay, to power of the source to the DC, and that DC directly connected to your bus. Okay, so that's why it is called the DC bus. Here you can able to see it's your DC bus. Okay, so this is your DC bus. Okay, so here you can able to see the solar photovoltaic as a renewable energy. The solar photovoltaic means PV panel, and the wind, both are connected over there. Okay, so from the solar photovoltaic, whatever it is converting, the output of the solar is coming the DC. So that DC should be compatible with the bus voltage. Okay, so that's why the DC to DC converter is required for boosting up the voltage. Okay, basically you know like that based on the, if you check the rating or the data sheet of the solar photovoltaic, so you are having an idea about that open OCC voltage. Okay, OCC voltage. So how much it is coming, based on that when the load is connected, how much voltage is coming with the current rating, based on that you are connecting with the DC bus. Now based on that we are having some protocols. IEEE, we are maintaining the IEEE protocols. Based on the protocol we are having some standard voltage of the DC bus. Normally we are designing it for the 48 volts. Okay, and your generations of the solar photovoltaic is coming nearer to 31 volt. Now if you connecting the solar photovoltaic to your bus, so what happens, that voltage difference is there. So that's why one DC-DC converter is required that can boosting up the 31 volt to 48 volt. Sometimes what happens, multiple solar photovoltaic cells are connected, maybe series combination, parallel combination. Okay, so based on that what happens, so it's having based on the converter. Okay, so it can be stepping up or stepping down. Okay, so some of the cases we are also using the buck boost converter. Okay, but buck boost converter means so both the operation can be possible, buck mode operations and boost mode operations for the AC. Okay, so here we can able to see that AC-DC converter for the wind system. Now output of the wind is coming AC. So as you know, it's a DC bus for the DC micro. So you have to convert the AC to DC. That's a AC-DC converter is required. Okay, so this part is for the storage purpose. Sorry, renewable source purpose. Now, as we have told that that renewables are more of the cases, the intermittency is their common factor. That's why we have a reliable storage module. Here we can able to see for the reliable storage module. Who are the key factor of that? Battery is there, supercapacitor is there. Sometimes we are also coming with the electric vehicle. That part I am coming. Okay, so battery means what? You know, like that different types of battery can be available in the lead acid battery commonly used for that. Now lithium ion battery is there. So lithium ion battery normally using for the vehicles. Okay, for our common microgrid, if you see in your home, so inverter battery we are using. So it's a lead acid battery. Okay, so again the DC-DC bidirectional converter is there. So this DC-DC converter is there. This is a bidirectional converter. Here the DC-DC converter, AC-DC converter, both are unidirectional. But here the storage and the grid and the bus, all those things are the bidirectional converter. So battery can be discharged through that path, through the converter to the bus, as well as battery can be charged from the bus to the battery through this converter. So BDC, bidirectional converter, is there for the transmission of power both on the side. Okay, and one thing is that the supercapacitor, the rise time, or you can say like the transient response of the battery is not good. Okay, so it is taking some time to reach the steady state value. So energy density is better, but the power density is not good for the transient purpose of the battery. That's why for maintaining the transient purpose, so we have to depend upon some of the additional component that is called a supercapacitor. So it's having good power density, but it's not having good energy density. So for the transient purpose, it can handle in better manner. That transient will be saved by the supercapacitor and giving the boosting of the power to the system. Okay. So by that way, so transient part will be taken care about by the ultra capacitor or the supercapacitors and maintain the stability. Now electric vehicle, how it is coming inside of the storage module. Okay, sometimes what happens, evening time. Okay, so evening time, so we are having some peak demand to our home. That time the vehicle battery can provide the power feedback to the system, DC bus system. Okay, and when the load is shedding, okay, on night time, so vehicle can be charged. Okay, so both the way it can be done. And in the load side, you can able to see it is your output load. Load can be AC load, DC load. Okay, both the cases some converters are required for connecting the loads, and AC supply module also be there for the utility grid. If anything required through the circuit breaker, so one converter is required, AC-DC converter, so that can connect it to the microgrid and we can able to see the results. Now we are coming about the AC microgrid. So here we can able to see the comparison between the AC microgrid and the DC microgrid. So both the cases we can able to see the comparisons. Okay. So it is your AC microgrid, it is your DC microgrid. Okay, so in case of DC microgrid, what happens? Whatever sources you have, that is converted to the DC and feed to the bus. And in AC microgrid, what happens? Whatever sources you have, that can be converted to the AC and feed to your AC bus. So AC microgrid, you are having AC microgrid, you are having that AC bus. Okay, and DC microgrid, you are having the DC bus. Okay, so only the converters are different. So solar photovoltaic will be DC to AC conversions required. Okay, for wind AC to AC conversion, bidirectional converter DC to AC. So then feed to the AC bus, and the load is there. That load can operate AC to DC and feed to the load. And AC to AC load is there, that directly feed to the AC load. Okay, and it's your main grid with the circuit breaker. Okay. And for the DC bus, same thing, whatever sources you have, so it's converted to the DC. Instead of DC to AC converter, you are using DC to DC. Okay, it's a AC to DC converter. Previously, here AC bus, it is a AC to AC converter. By that way, it can be operated. Okay. So in this case, what is the problem? So unnecessary, you are changing different types of converters, so that may cause for multiple stages of power changes and unnecessary power losses. That's why the concept has came. It is called that hybrid microgrid. So what is the motivations of the hybrid microgrid? So whatever DC sources have, that can be connected to the DC side. Like like here, if you are having a DC bus, okay, so DC bus is connected. So whatever sources you have, suppose solar photovoltaic, everything will be connected to the DC bus. Okay, and whatever here you can able to see, it is a solar photovoltaic. Okay, so that is connected to your DC bus through the DC-DC converter. Battery is there, that also be connected to the P batteries to the DC bus, and the AC sources like wind, okay, wind, diesel generator, or something utility grid. Okay, AC load, in case of DC load also be there, DC side, so that can connected to the AC bus. So in between AC and DC bus, there is a bidirectional inverter, or it is called that interlinking converter. Bidirectional interlinking converter, that can be transfer the power from both AC and DC bus. That's the concept of the hybrid microgrids. Okay, so it can give, currently the hybrid microgrid is the very common aspects, and it is used for that several applications. Okay. So what are the protocols? What are the converters? From that study, you can able to see different types of converter we are able to understand. First type of converter is your interfacing converter. Interfacing converter means that power electronics converters are the key factor for integrating your renewable sources to your AC bus or DC bus. Okay, so that's why it's an first concept of converter is that interfacing converter. Okay, so that can connect your renewables to the system. Second type of converter is your bidirectional converter, like DC-DC bidirectional converter. Okay, that can transfer the bidirectional power flow in between your storage to the microgrid. Okay, another converter is there which is known as interlinking converter. Okay, so that can be interlinked between your AC bus for the hybrid microgrid, AC bus to the DC bus. So there also the bidirectional power flow can be happen. Okay, so now that lot of power electronics converters are there, and the control unit is there that can generate the gate pulse based on your requirement and drive your converter to transmissions of the power from one direction to the another directions. So as you know that different power electronics converters are connected and different types of load can be possible. So DC load, AC load, sometimes non-linear load. So power quality, power quality issues also be very important factor, because that all the power electronics converters are working in the non-linear modes. Basically, what are the converters we are discussing over here? So they are working in the switching mode power conversion, not in linear mode of operations. Okay, if they are working in switch mode power converter concept, so it having some issues of non-linearity. What type of non-linearity? Switching non-linearity. If the switching non-linearities are there, okay, so that can that can be caused for different power quality issues. Okay, that's why we have to follow some IEEE protocols. Okay, for the standardizations of your system. Suppose you are prototype, you are designing a prototype. That prototype is it reliable for that applicant end or not? That also be very much important. So that will be decided by basically the based on that how much the power quality issues are, how much that based on the protocol it can be decided. Okay. So flowchart of the designing of the power electronics converters. Okay, here we can able to see. So first we have to select the topology. Okay, so topology means what are the applications you have. Based on the application, you have to select the topology. So the steady state behavior. So if you see the control dynamics of the system, so steady state behavior normally decided by the topology of the converter. Okay, and that transient condition normally decided by the whatever control topology you are using, whatever controller you are using, based on that you are selecting the transient concept. Okay. Then the mathematical modeling. Why the mathematical modeling is important? Basically, the converter, whatever we are telling the name of the different topologies of the converter, they are highly nonlinear. Okay. So mostly you are designing the controller. Okay, right now the digital processor, the digital transform, digital computers. You are considering different type of. You are designing the controllers inside of your computer. Okay, so that's why some real-time system can be interface with your practical systems. Okay. So whatever controllers are there, that should be the mathematically designed by yourself. If you accurately model the converter, okay, then only you can able to design the controller in accurate manner. If we are not able to perfect modeling of our converter or the topology of the converter, so if there is any model mismatch, so the error, whatever error you are considering, the practically the error will be more than of your actual value. The efficiency of the overall system will be reduced. So that's why the mathematical modeling is very much important. Based on the mathematical model, accurate mathematical and sophisticated mathematical model, you can design the controller. Okay, which control scheme you are going to design, and finally you are able to implement it. Okay, so first thing is the topology selection, then mathematical model, then control system. Okay, and finally the implementations of your controller. Okay, so in the control system, after that what happens, you have to maintain. If the entire process is completed, implementation means first we are going to the software implementation. After that, after verification of the software implementation, then we can go for the experimental implementations. Okay, so based on that, first we have to see the different control aspect. First we have to check the good line regulations, good load regulations, good transient response. Finally we have to see the stability of that applications. Okay, so line regulations means what happens, so we have to see that properly any disturbances are coming in your input side. So how much, basically we are not considering very more disturbance in the input side, so it can disturb the system any drastically. Okay, so that's why we have to consider there is a percentage of consideration, not more than 5%. Okay, so whatever disturbances are coming your input sides. Okay, suppose solar photovoltaic, any disturbances means suppose there are different conditions. Okay, solar irradiance, temperature, sometimes shading conditions. Okay, so how the output will be maintained constant. Okay, so that is the challenging job. It's called the line regulation. So load regulations, any changes happen in your load side. Okay, so load disturbances are there, so how the output will be maintained, that will be decided by the load regulations. Transient response is there. Okay, so transient response means how fast the converter is responding. Any disturbances came, so how fast the converter is responded. Basically it will be decided by your control scheme, what type of control scheme you are using. Based on that, finally the stability analysis we will do, how the converter is behaving. So for that one, we have to do some modeling aspects of the switching converter. As we told you, it's a nonlinear time varying system. So you have to design the converter such a way, so it should be the linear LTI system, linear time invariant system. Okay, for that one, we are having some different steps. First, we are writing the on state and off state differential equations based on the switch on and off. Okay, so we are having some set of equations here. We can able to see that some set of equations, okay, for the on time as well as the off time conditions. Okay, then it is your output equation. So finally we have to decide the state variable. So minimal number of variable that can decide the state of the system, that is called the state variables. Okay, so here we are considering the inductor current and the capacitor voltage as a state variables. Okay, then what we are doing, we are using some averaging method, state phase averaging method. Okay, so that's why where on time and off time equations are there. So now we are averaging them. Okay, finally after averaging, what happened, we are going for the perturbations. Okay, so whatever variables are there, so we are perturbation means we are considering that variable having one DC component, one AC component. Okay, so based on that we are replacing in the equation. After that we are having an identity. Okay, so we are separating the DC component one side and the AC component one side. From the DC component, if we are equating, so we will get the steady state gain of the system. Okay, and from the AC component means small ripple factor component, so that will be written separately, and after that you will do the Laplace transformations, and finally you will get the Planck transfer function of the converter. Okay, it's a generic transfer function. Here you can able to see. Okay, so it is a generic, so it is a Planck transfer function of the converter. Any converter you can able to design. It's a control to output Planck transfer. Okay, so now it's a block diagram, it's a closed loop block diagram of the switching converter. Okay, so where we are giving some of the reference voltage. Okay, so reference voltage and it's your output voltage. Okay, so your output is there. Suppose we are taking an example, we are just taking an example. Suddenly your output, basically we are maintaining the energy constant. Energy means it's an integrating factor with the time into the power. So energy is a power into time. So both sides the energy is constant means power input as well as power output. Power input equal to the power output. Okay. So we are maintaining the power constant. Suddenly any situation happened that load demand has more, means output voltage. Okay. So what happened with the output voltage? Load is more means sometimes what happens, so as an electrical engineer, high load is more means the current. Okay, just suddenly current is high. Okay, so now if the power is maintaining constant, okay, if power is maintaining constant, so current is high means, so voltage, output voltage will be dip. Okay, dipping of that output voltage, so V0 value will be dipping. Okay, so now what happened, what is the process to maintaining that thing? So what happened, the error, here you can able to see the here you can able to see the error. Here the adder block is there, minus is your, it is your output and it is your input. My reference, it is called the set point tracking or the reference tracking. So you will get the error signal. Okay, so now compensator or controller is there that is trying to minimize that error. Okay, it is trying to nearer to the zero. Okay. Now the PWM controller is there, PWM, so it's an it decide the switching frequency of the converter. Okay, the frequency of the PWM, so it's comparing with the error and you will get some PWM. That PWM will be feed to your switching converter gate pulse. Okay, and the converter will be operated. Okay, so if the voltage is reduced, so you have to find out the fix up the logic such way. So converter, if the voltage is reducing, the converter on time duration should be high. If more, if it is less, then it will be unstable condition. So again reducing, then converter will be off. So for the stability, it should be like that. So dipping more means switching pulse with also with more. Okay. Now interfacing converter, so we are having different types of converter. So first we are talking about the interfacing converter. So this is a feed forward control. So basically, you know, like the solar photovoltaic is using, so it is IV characteristics. Okay, solar photovoltaic. So we are fetching the voltage and current and feed to the MPPT algorithms. Okay, so the switching converter is using over there. The gate bus of the switching converter basically basically run through that MPPT. The gate pulse will be decided by this MPPT algorithm. So what is the MPP point? So maximum power points based on that duty cycle fixing up. So you have to fix the duty cycle such a way maximum power should be tracked. Okay, like that. Okay, and it's in common structures. Okay, so for the MPPT here you can see this is your MPP region here. So the gate pulse you have to duty decrease this side and this is duty increase. So VMPP point you will get the maximum power over there. It is VPV and it is PPV. Okay, you have to find out the maximum power. Okay, so reducing that side it is increasing. Okay, so it's your common structure. So here you can having the solar photovoltaic with the battery storage. So our concept of DC-DC converter is that will be run through that MPPT. Okay, and it is your DC bus voltage. That bus voltage is maintained constant by this bidirectional converter. It's a battery unit, DC-DC battery converter. That battery unit is there that is maintaining that bus voltage. Okay, it's an electric vehicle and the first charger is there, so based on the battery can be charged and overall control will be decided by the rule-based algorithm. Okay. Now for that, as you know, like that the voltage is less, okay, and your bus voltage is 48 volts. So what happens? We have to use some, in that case, boost converter. So boost converter is an example of a switching converter. If the voltage is more than of your bus voltage, so you have to design that buck converter. And if the voltage is more than that, sometimes more and sometimes less based on the series parallel combination, so you have to design some of the buck boost converter. Okay, so here we are using some state phase modeling approach for the boost converter and buck boost converter and switching converters. Okay, first based on our previous discussions, we are using the set of differential equations. Okay, for that mode of operation, mode 1 operation, this is our mode 2 operations. Okay, based on that KVL and KCL. Okay, so we have to design some set of equations. Okay, as well as mode 1 and mode 2, and that set of equations is the differential equation, on time equations as well as off time equation. Then next step what we are doing, these are output equations. Okay, and then what we are doing, we are having a averaging. Okay, duty weighted averaging for on time equation and off time equations. Okay, so this is your average equation, state equation, and this is average voltage equations. Okay, then what happen, you will do the we are having some, previously we are having the plant transfer function directly. Okay, so you replace those value A, B, C, D value. Okay, so for the plant transfer functions, and finally we will get the transfer function of the boost converter. But what happened, the boost converter having one problem, that is called in the control to output function you are having a RHP 0, right hand plane 0 here, this component. Okay, RHP 0. So boost converter is an example of a non-minimum phase problem, non-minimum phase converter. So what happened with that one? So due to the non-minimum phase, why it is called the non-minimum phase? So you can able to see it is a second order system. Okay, so two poles as a denominator. Okay, so that poles can contribute minus 90 plus or minus 90, so minus 180 degree, but as 0 is in a right hand side, so that's why it can also provide you another minus 90. So system, if you draw the Bode diagram, okay, so if gain plot, nothing problem has came, okay, no reflection has came, but in the phase plot, what happened, you can able to see that due to the 390, so it's a minus 270, that Bode diagram, the phase plot, it is coming to touch to the minus 270 degree. Okay, phase delay. So that's why it is called the non-minimum phase problem, means maximum phase delay system. For that one, what happened, initial undershooting is coming, so that can sluggish your response. Okay, suppose the disturbance has came and initial undershoot, your converter should reach the set value very fast, but initial undershooting is come, so that undershooting means what happened in the control loop, previously block diagram we have shown. So output voltage is there, that output voltage is compared with your reference value giving to the plus point, and that output voltage is coming to the minus point. So reference voltage minus output voltage. Suddenly due to non-minimum phase, what happened, that output voltage is coming with the undershoot, means it automatically it is negative. So your reference value minus of minus output means adding with your reference value. So it's a high chances for the positive feedback system. So positive feedback system cause for the instability of the system. That's why there is a problem with some dealing with the non-minimum phase issue. Okay, so we have to design some special type of controller for avoiding or for minimizing the effect of the non-minimum phase. Okay, next case also buck boost converter. If voltage can be more than of your DC bus voltage or the less than of your DC bus voltage, you have to design the buck boost converter. So similarly, in this case, we are using in this case we are using that mode on operations and the mode to operations, both the cases that on time equations and off time equations. Okay, both are connected over there. Okay, so sorry, both are writing over there the set of differential equations. Now what we are doing, we are doing the similar process state phase average model means where duty based averaging method we are using for mode on and mode 2 operations. Finally, we are having some set of equations like plant transfer function. This is your generic structure of the plant transfer function, and after replacing the value of a, b, c, we will get the plant transfer function of the buck boost converter. Okay, in this case also one RHP 0 is present in the right up plane 0. Okay, RHP 1 right up plane 0 is present in the plant transfer function. So that may cause also the non-minimum phase problem. If the non-minimum phase issue is there, similar kind of issue is that boost converter. So whatever interfacing converters are using for the DCC converter, basically boost converter, buck boost converter, different derived converters, derived topology of the buck boost converter, especially the SEPIC. Okay, so all those cases the non-minimum phase problem has came, and we have to sort out the issue, or we have to dealing with the non-minimum phase problem. That's why what happened, we are from the literature we have received one good I have received one controller that is called the type controller. It's a type controller means there are three types of controller: type 1, type 2, type 3. Okay, type 1 controller is just like a integral controller. Okay, here if you see the type 1 controller plant transfer function, you can able to see it's one pole at origin only. So it's an integral controller. Okay, but type 2 controller, it's an integral controller cascaded with some lead controller. Okay, why we are using the lead controller? Basically, lead controller having the capability for the phase boosting capability. Okay, as you know, like that is an example of a non-minimum phase problem. So if we see there, phase delay will be there up to minus 270 degree. So if you are using some cascaded with some lead compensator, so what happened? There is a inherent capability to boosting up the phase of your plant transfer function of the converter. So that's why the lead compensator cascaded. Why the PI compensator is there? You know, like that sometimes the lead compensator are not all times are not nullify the steady state error sometimes. So that's why the integral controller also been cascaded with the lead compensator. So it can also nullify the steady state problem, or it can be steady state error. Okay, then type 3 compensator also be there. So type 3 compensator what happened? So similarly type 2 compensator, additional lead compensator is connected. So two lead compensator cascaded with two lead compensator with that integral. So both the lead compensator can phase boost up to 180 degree. Okay, and one integral also be there that can also be used for the reducing the steady state error. So that's why the type 3 compensator can be used for this non-minimum phase problem. Okay, I hope up to this time, up to this point, we can able to see that we can able to able to understand the problems. Now the real-time experimentations. Okay, so from that one we are dealing with the non-minimum phase problem with some control aspects. Okay, so type 1, type 2, type 3 controller we are using, but now we are talking about dealing with the non-minimum problem with some topological aspects. Okay, basically boost converter having one control switch, another one is uncontrolled switch. Okay, and we can able to see the literature. We can understand that inductor of the boost converter is play the key role for that non-minimum phase problem. That's why what happened in tri-state boost converter. Okay, in tri-state boost converter, what we are doing? So one additional switch here. one additional switch that is called the freewheeling switch with the freewheeling diode is connected anti-parallel with your inductor coil. Okay. So what happens that switch will be used, switch will be turned on, and it trying to discharge the energy of that inductor. Okay, so for that one, it can be able to see some of the instant that inductor voltage is 0. Okay, and from the study, we can able to understand that the non-minimum phase problem can be nullified with that one. So some experimental results, it's an overall setup. It's a tri-state boost converter. It can be observed over there. Some experimental results we can able to see the steady state response of tri-state boost converter. Okay, and the transient response of the tri-state boost converter with the resistance and load changes. Okay, so it's your output voltage. Okay, and the variations, input current variations and load disturbances are given. So from there, almost the regulations are maintained with some minimal source. Okay, so based on that, we can able to see. Okay, with type C compensator. Now, what is the problem with the tri-state boost converter? Their response time is not good as like the boost converter. Okay, so because of the topological aspects, topological nature. So another concept is coming. So it is called the interleaf converter, interleaf boost converter. Okay, in interleaf boost converter, what happened? Okay, so in interleaf boost converter, boost converter, what happened? Two boost converter connected look like a parallelly connected, but it's not a parallelly connected. It's a interleave mode of operation. Means interleave connections. Suppose for the both the switch here you can able to see the both the MOSFET switch are there. They are connected. They are operated alternator manner, complementary manner. Means when this switch is on, this switch may be off. When this switch is on, this switch may be. There are four modes of operation. Okay, and you can able to see the current pattern. Okay, inductor current pattern. Okay, so complementary. So when one inductor current is high, another inductor current is low. So complementary effect. So in input current, if you see the input current, so their ripple will be less. Okay, the ripple will be less. So power quality increase. Okay, the ripple will be less, so its quality is increase. And the gate pulses we can able to see from the experimental study, and output voltage. So it is single phase inductor current, and this is the input current. So both the ripple cancellation we will get this one. Here we can able to see the load regulation. So very first response we are able to see that two disturbances happen with the changes of the load resistance. The setup we can able to see. Okay, with that tri-state with that interleaf converter. So what we can able to understand, tri-state boot don't have the non-minimum phase problem, but their response is not up to the mark with the boost converter. So in interleaf boost converter, as it is derived from that boost converter, so it's, if we see their transfer functions, okay, so their response time will be very good, but the main problem is the non-minimum phase problem. Okay. That's why we have proposed some new converter that is called the tri-state interleaf boost converter. Okay, so new converter, that is your tri-state interleaf boost. So in this case, what happened? So both two tri-state boost converter are connected in the interleaf mode, and their operations will be done. Okay, so their operations, if you see, it's intermediate conditions in between your interleaf boost converter and the tri-state boost converter. For the voltage step-up ratio versus input current ripple, this is input current ripple. Okay, and this is voltage step-up ratio with the output voltage ripple. Okay, from the experimental study we are able to get. So this is your experimental study. So it is your current pattern. Okay, as well as the voltage pattern, gate pulses are there. So basic operations. Okay, I hope till now we can able to understand about the interfacing part. Now AI applications for the power management of the microgrid. So why those converters are important? So converters are basically using for that power transmissions from your input for interfacing of your renewables to your microgrids. That's why the dynamics, converter dynamics, and the controllers of the converter dynamics are very much important. Now the AI applications are coming in the picture. So you are having several number of renewable sources. So how they are responding with the different, how they are responding with the different sources. That's why the AI applications are very much important. So what are the important factors for that one? So demand forecasting, okay, energy generations optimization. So how optimally you are designing, load balancing, okay, so predictions, predictive maintenance. Okay, so these are the energy storage management, grid resilience, market interaction, cyber security, and even. So in this case, we are giving that more focused on the energy storage management for the AI application. Means we are designing some of the intelligent controllers, okay, for that purpose. So different algorithms also available in the literature. So what are that one? So reinforcement learning, RL, predictive analysis, generic algorithm, fuzzy logic based controller, particle swarm optimization, neural network, model predictive control, game theory, swarm intelligence. So different algorithms also available. In this study, we are using basically fuzzy logic based lab. Okay, so PSY results are not there, and the neural. Basically, we are talking about ANFIS, means neurofuzzy based application for this here. So first we are starting with that MPPT. Basically, there are different MPPT's algorithms are available like PNDO, INC. These are the classical method. But in this study, we are using ANFIS, means adaptive neurofuzzy interfacing system. Okay, so there are different fuzzy based rules are there. Okay, for different parameters. Okay, so here we are using different parameters. Okay, fuzzy based parameters were decided. So different inputs are coming. Okay, different duty weights are there, and we are calculating the output one. Okay, so here finally we are having some of the logics. Okay, this is our example for a some adaptive example, some of adaptive neurofuzzy interfacing system. So we are using NFIS toolbox. Okay, and it is your membership functions. Okay, different levels are there, level 1, level 2. Okay, finally this is your DC link voltage. This is the simulated results. Okay, so where we are able to see that DC link voltage is maintaining constant. It's a fuzzy logic based and phases. Okay, so here you can able to see in MPPT algorithm. So NFIS modulated PV is there, temperature is there, so both the PI controller there, so control signal, so where comparison, and finally PWM will be there. So based on that, we are driving the switching converter to get the results. Okay. Now another phase of applications is a DC-DC bidirectional converter. Suppose your battery voltage is 12 volt. Okay, two batteries connected in series, so 24 volt, and your bus voltage is 48 volt. Now your bus volt is trying to your battery is trying to discharge through your discharge through the converter to the bus voltage. Then what happens? Okay, so if it is on to discharge to the bus voltage, so you have to change from 24 volt to 48 volt. So boosting mode of operations are required. Okay, for discharging the battery. Okay, and reverse thing, if the battery try to charge from the bus, so 48 volt to stepping down to 24 volt. Okay, and it is charging mode of operation. So what you have, so here you can able to see this is boost mode of operation. So battery is there. So one switch, this is control switch, and control switch, DC link voltage. Here the DC link voltage is there. This is your control switch, and control switch buck converter battery. So both the mode you are cascading. So you are having a bidirectional buck boost converter with the battery. This is your coil, and that bidirectional switch you are using over there. So it is your PV array. Now the load is connected, and it's a hybrid bidirectional like that. It's your bidirectional switch. Okay, inductor is there, capacitor, it's a battery. Okay, this is the operations. Okay, both full bridge operations can also be possible. Now different modes of operation, single phase shift, dual phase shift. Okay, so different shifting can also be hybrid converters. So both AC DC we can able to get from the supply. So it's also available. Okay, now we are going for some algorithms. Okay, so and some results on that. So maximum power point tracking algorithms are say there. So it is DC converter, solar photovoltaic source is there, MPPT algorithm. So we are maintaining the DC converter, controlling the MPPT algorithm, the DC converter. Bus is there. Now we are trying to maintain the bus voltage. So from the MPPT, it's not like that bus voltage also being constant. No, it's not possible. So you have to maintain additional loop voltage loop to maintaining the bus voltage constant with variation of your load that happened over there. Okay, so controller block diagram is there. It is your bus voltage reference. It is bus voltage, actual bus voltage is reference bus voltage. So voltage controller is there. You will get the PWM to control the converter. So it's some results are there with the constant output voltage under different conditions. Okay, so solar irradiance has changed. It's a abrupt changes are given over there. Okay, but practically it's not like that. Practically some gradual changes are there. It is the radiation level. It is your temperature level. Okay, changes of that without voltage controller. So green line is your without voltage controller. So voltage is varying, fluctuating without voltage controller. And here MPPT also be there and voltage controller also be there. So trying to be maintain the fixed. Initial high overshoot is there. After that, it is maintaining fixed. Okay, it's some IV characteristics with variation of the temperature. This is IV characteristics and PV characteristics with variation of the solar. So now we are focusing on the results of some bidirectional DCC converter, where we are using two loop operation. This is half bridge bidirectional configuration. So that we have already shown you some of the previously the topology. Okay, battery is there and it's your DC bus voltage is there. Now bidirectional DCC converter using dual loop control. Okay, V bus plus minus voltage controller. So error is there, then that will be the current reference and comparing the current. So current control, you will get the PWM. So similar process, we will do the state phase average modeling for the bidirectional converter, and finally we will get some with having some value. So V bus 220, 240 volt, 15, 20 kilowatts. So finally we will having some transfer functions. Okay, transfer functions. Okay, and based on the transfer function, we are designing the voltage controller and the current controller with the CISO tool of the MATLAB. Okay, after the CISO tool, so we will get some KP and KI value. Okay, for the voltage controller loop and the current control loop. Okay, KP and KI value. So it's your battery current. Okay, so if the current is changing from minus to 0 and then 0 to positive. So what I mean SOC level. So minus current means current is battery is charging. So that's why SOC level also means gradually increasing with having some slope. Then plus current means it is decreasing, meaning discharging. So SOC level is discharging. So it is your battery voltage. Okay, so maintaining that way based on that current and voltage. As the power is constant, so current and voltage are almost complementary. Okay, so current is battery is charging means current is negative. So now voltage is more, then gradually reducing. Okay. There are four mode of operation for the islanded DC microgrid concept with the solar. We are having two set of results with some DC microgrid results. Another one is some hybrid microgrid results. Okay, so here you can able to see the block diagram structure of the DC grid system. Okay, so PPV is the power generated by PV. P load is the load power. There are four modes of operation. Mode on operation when PPV equal to P load without storage. Mode 2 when PPV is greater than P load with storage. Mode 3 is that when PPV less than your P load with storage, and mode 4 is PPV is varying with the storage. So four modes of operation. First condition PPV equal to P load. So with the changes of the solar photovoltaic, here generation has changed. Okay, generation has changed, so load power also been changed according to that. Okay, so load power is changed means more load means current is increasing, so voltage is decreasing. Okay, you can able to see the voltage is decreasing. Second mode of operation, mode 2 operation, islanded mode with that. So PPV is greater than P load means PPV minus P load, some additional power will be there that will be coming to the battery. So battery is charging. Okay. So here you can able to see that 11 almost 12 kilowatt of your PV generation is there. So but your load power is now it is 4 kilowatt. Okay, so 12 minus 4 8 kilowatt, or it is 11 kilowatt. This is 4 kilowatt. So 7 kilowatt. So 7 kilowatt power coming to the battery. Okay, so that's a minus. Power is minus. So current also be minus. Basically, battery is charging. Then next step here you can see this is 6 and this is 11. 11 minus 6 5. Okay, so it is minus 5 kilowatt, almost nearer to that. And finally both are same, it is 0. So current also been negative to 0. Here you can see the current is coming negative, then again less negative, finally it's zero. So SOC level also been increasing based on the current changing. Okay, so SOC slope you can able to see it has increasing like that. Okay, then finally it is steady. Voltage is dipping, current is increasing means here you can see current is increasing, so voltage is dipping. But load voltage is maintaining constant. So who will maintain the load voltage constant? The bidirectional power. The controller controlling the bidirectional converter, or voltage and current loops are there that can maintain the load voltage constant. Now third mode of operation, in this mode what happened? In this mode you can see that islanded mode, boost mode. So PPV less than P load. Okay, means you can able to understand that PPV in generation power is less than of your load power. So P battery equal to P load minus PPV. So additional power is coming from the battery. So here you can able to see it is 11 kilowatt generation constant. Now your load power is almost 11 kilowatt. So generation 11 kilowatt, load power is also 11 kilowatt. So as per the power management algorithm, so what happened, minus thing will be there. So battery power is 0 kilowatt first. Then second, after 2 seconds, what happened? It is same, generation is 11 kilowatt, but your load power is increased to 13 kilowatt or 12 kilowatt. Okay, 12 kilowatt almost. So 2 kilowatt additional power will come from home, from the battery. Then the rest of the thing also, the 6 kilowatt, it is going to 16, it is like that. Okay, 16 it is 10 like that. So automatically additional power is coming from the battery. So current also we follow the power path. So initially current is 0 here, then increasing, again increasing. So SOC means battery is discharging. Current is positive means battery discharging. So SOC also will reduce in such a. Voltage also will following that one. So battery is current is giving, battery voltage is decreasing, but load voltage is maintaining constant. Third mode of operations, both are changing. So solar power has generation, solar generation has changed because you are changing the irradiance, but constant load power is fixed. So solar radiance has changed on 2 seconds. Okay, so generation drastically reduced. So if the generation that point is transient, so automatically at that condition transient load point has reduced, then again come back to the steady value. Okay, at that point initially the power is negative for charging, then it is discharging power is positive. So SOC initially increasing, then that 2 seconds decreasing. Similarly, the current is also following the power in negative, then it is positive. Battery voltage also be coming like that. So voltage is maintaining fixed. Okay. This is the basic prototype of the bidirectional SEPI converter. Okay, it's a open loop applications you can able to see over there. Okay. Now we are discussing about the hybrid microgrid and their and their power management algorithm. So it's your structure of the hybrid microgrid. This is bidirectional interlink converter. So we are designing the controller to controlling the gate pulses of this bidirectional converter for maintaining the power management of the storage. So different multiple sources are there. Okay, so multiple solar, wind farm. Okay, this is the schematic diagram of the microgrid system with having some values are given. Okay, system parameters are there, system configurations. Okay, control block is there. Okay, so it's your battery and hub bridge converter is there for the bidirectional power flow. This is your load. Okay, source is there and this is the receiving point. So again we are using the same process for transfer functions. Okay, of that one. So we are having several case studies. For case one is there for the under variable load power demand with the constant generation. So first generation is constant. Okay, here you can able to see the PPV. PPV that is a constant ordinary generation, but P load is red color. P load is gradually increasing. Okay, so if P load is gradually increasing, okay, so P load is gradually increasing. Okay. So P load is gradually increasing, but who will take care about the additional thing? That P battery. That battery will take care about that thing. So here you can able to see P load and the battery is there. Okay, so following that part. So SOC diagram here you can see this is your SOC diagram. Okay, how the SOC has changed. Here you can see the how the battery power has changed. Okay, PV battery and current battery and this decelerating wheel. The spikes are coming. The spikes are coming because of the load variations. Okay, this is your demand for the constant generations. Next case is the constant load power with the variable solar irradiance. So solar irradiance has changes here. You can see the solar irradiance has changes, but P load is constant. But PPV based on the changes of the irradiance, so PPV has changed. So wind also been constant, battery also moving, changing based on the requirement. Also the DC link voltage you can able to see it is your SOC level. Okay, SOC level is there to understand their process. And finally the system performance is the under variable solar temperature with the constant load power. So again the load power is constant, solar temperature has changed, so solar temperature variations are there in variations because of the variations generation solar photovoltaic generation. This is the solar photovoltaic generation. It has also been varied. Finally here you can see the battery also being changes and it is your SOC level how it has changes you can able to see and battery kilowatt changes. Okay, then the wind speed variable the wind speed and constant load power. This is the constant load power. Okay, and the wind speed has changes. Okay, this is the P battery with the wind speed is changing over there. Okay, and how the receiving voltage is maintaining constant. Here you can able to see. Finally, all the parameters are changing, like under variable wind speed, variable solar irradiance, variable temperature, and the constant load power. So load power is constant. So all those things are changing. So battery, you can see battery power also being changing. Finally, the receiving voltage is also being trying to be maintained nearer to constant. Okay. In this figure, all are changes. So variable wind speed, solar irradiance, solar temperature, and variable load power. Okay. And you can see the battery DC voltage also being constant. Okay, now power management scheme for hybrid storage system. So it's the power management algorithms. Okay, for the hybrid storage conditions. Okay, so we are using the intelligent controller. Okay, like fuzzy based controller we are using. So for the hybrid microgrid concepts, here you can see the architecture of the hybrid microgrids. Okay, solar photovoltaic, wind, battery, and supercapacitor we are using, and it's your surface diagrams. Okay, so adaptive fuzzy controller is used for the multi-state ROPID controller and your quiver view of the FLC controller, fuzzy logic controller. So several things, same thing we are changing with the variable DC microgrid voltage level. So here you can able to see the spike. The spikes are coming only for the supercapacitor. Okay, so supercapacitor working fine. That's why it is working in transient mode. Then finally you will get the steady value. Okay, all the cases you can able to see the spike of the supercapacitor. So variable generations of the DC micro. When conditions are given based on that it can be worked. Okay. SOC level, this the SOC level diagram. Okay. Another variable load with the hybrid microgrid. So load you are changing. So how it is followed. Robustness study of the parametric answering study, whatever. Different studies they are given with the results. Okay. This is our lab photograph for the advanced power processing laboratory. Okay, so we are having a funding of the DST. Okay, seed division. For that one, we are designing or developing different type of setup for our applications. And some control aspects we are also telling over there. Okay, so as you know, like that now coordination controls or graph theory based control are very much well popular. So you are having a multiple DG, different distributed generation. So there is a coordination between different sources are very much important. Okay, from there we can able to coordinate them. Okay, and different controls are there. So there are three types of control we are able to see. This is decentralized control. Another one is centralized control, and finally distributed control. So in decentralized control, you know, like that there are individual converters are there. On the individual converters, you are controlling the converters. Individual controller you are there. So based on the they control. So there is no coordination between the two local control. LC means local control, and DG means your different renewable sources of the converter. Okay, so that's why what happens, you can be able to state the centralized control. So one microgrid central control is there. From there you are generating the local control. But what is the problem with microgrid central control, centralized control? So there is a high chances the system will be more complicated, and there is a high chances for sometimes failure of the system. That's why you have to go for some distributed control. So where that is also known as the coordination control. So there is a coordinating between two local controllers or all the local controllers. Okay, that's the good thing for the applications. Otherwise, there is some group control. Now we are working on some uh, oscillatory based control. Different control aspects are famous in that microgrid. So it's a very limited time, and it's a very vast area. Whatever we have done on that, some very basic thing we have discussed. There are other several works are there. We can able to demonstrate over there, but due to the time constraint, some key features and some from the crash level to some research level, I have discussed over here. So for that, I definitely have thanks to my different students. Those are working. We are associated with work with the students, and it's a collaborative job. So definitely, I'm thanking over on them. So they are giving their day and night effort for designing different control aspects, as well as for the applications of the microgrids, different standalone system, power management. Thank you. Thank you. This is from my end. So if any are having any queries, please let me know so we can discuss on that.
Thank you, sir, for sharing your valuable knowledge on the topic Intelligent Power Management Scheme for Microgrid Application. We hope this will be really helpful for every participant for their better future. So now we are sharing Google Form link on the chat box for attendance come feedback. So please fill it after question and answers here. Before that, I am requesting every participant, if you have any question, you can ask one by one. So please raise your hands.
Sir, good morning, sir.
Good morning.
Sir, is standalone PV system comes under microgrid or not, sir?
Yes, standalone PV system we are considering for the microgrid.
Okay, sir.
Hello,
Hello, please.
sir. Good morning, sir. I have a question regarding sir. Sir, as you mentioned that there are lots of energy storage like capacitor, batteries, and other things, sir. How it is possible to operate means how to manage their operation at a time electric vehicle application, because all have different capabilities and features. Like lithium-ion batteries are very temperature dependent, and in case of capacitor it is has another feature. So to manage all these things at a time for electric vehicle application. Yes, sir.
Yes. So basically, basically what happened? So you are having a hybrid storage system. That's why the BMS, like that in vehicle, the BMS algorithm, okay, battery
Yes, sir.
management system algorithm is there. Okay, based on that, your priority basis. Okay, so now AIML having means AI based different intelligent algorithms are also be there. So it's called clustering. Okay, so somehow suppose in some of the battery temperature is high, because in that in the vehicle the storage is different in the vehicle. Suppose lithium ion battery you are using, so in that case the capacitor is not required, I think. So recent scenario, some type of lithium ion batteries are coming having very good transient response also. Okay, so in that case the storage packets are coming. Okay, so based on that, you are making some segments. Okay, and how the some of the storage packets are having fully charged. The charge also being very important, means how much charging ever there. So which one is not fully charged. The clustering is very much important. So that thing will be taken care about some of the algorithms. Okay, so intelligent algorithm you have to associate it with your BMS system, or that algorithm you have to develop by yourself to understand the temperature differences, or this battery having more temperature, so we can isolate the system, automatically isolate them. Okay, based on the battery health monitoring system. Okay, and the charge balancing are also very much important. Okay, which is fully charged, half charge, like that, which is in depth or discharge mode. Okay, so based on that, it totally depends how efficiently you are designing the BMS algorithm.
Thank you so much, sir.
Thank you.
Hello, sir. Hello.
Hello, please.
Myself, Supriya. Actually, I have one query, sir. Sorry, initially I was struggling for unmute. Initially, sir, in some of the slides you have shown that you have got non-minimum phase system. So how you have
Yes.
tackled that problem? Can you just give some light on this again, sir?
So non-minimum phase problem, basically we have to design some of that controller, that is called type controller, we can able to design. Okay, but we don't have money. We are not showing a lot of results, no results on the type controller with the converter. Okay, so if we show, if we are showing over here, so you can able to see the type converter cannot fully nullify the non-minimum phase problem. Okay, so type converter is using only for making the system dynamics very fast. Okay, that rise time may be reduced, as well as the peak overshoot also been reduced. That's why you are using some lead compensator. Okay, so both will be the trade-off. Okay, non-minimum phase problem may be there, but we can reduce the non-minimum phase problem somehow. Some parameter selection, sometimes some of the cases parameter selection. Okay, sometimes we are designing the pole right up plane zero, right up plane zero, and the left hand plane zero, both are in the mirror image. In this case, some of the cases non-minimum phase can be nullified. Then we are also using the type compensator or other compensator, so their response also being fast. Okay, type compensator normally using for making the system dynamics fast compared to the other compensator, like that. But that results we are not showing over here. Okay, so if we follow, we're having some of the work on that. So if you search on that, so you will get some of the work on type compensator. So you can
Okay.
follow that work also with having some
You
results.
told about the mirroring of that. So one of the paper actually I found it, but I wasn't sure is it okay. They have shown that the all pass filter can be used. So by mirroring
There
the
are several,
non-minimum phase pole
huh,
and then so what you will like suggest, sir?
there are several methods. Okay, I am telling you some feasible method. There are 4 or 5 feasible methods. There selection of the switching converter, that you are telling them filter designing. Okay, that I am telling right now mirroring of that pole zero locations. Sorry, zero, both of the cases locations. But among of them, some modeling technique also be there. Okay, if you follow some of the paper by Professor Bass, so they are using some of the modeling technique for minimizing that issue. But in our case, we are using some type compensator. We are also optimizing the parameter of the type compensator. So it is quite convenient. That's why so if you can also change the selection of the converter parameters, the non-minimum phase problem can be nullified also. But parameter selection is in your hand. Okay, but you have to design the system quite generic aspects, so your system dynamics can be fast. That's why the type compensator is better to use for your application.
Okay, sir. Thank you, sir. Thank you very much. I will try that.
Thank you.
Hello, Professor Arnav.
Uh,
I'd like to request you that we wish to wind up this session. if there is any query
Yes.
from the audience, they can just share it through
Yes.
email or something like that, because
Ah,
we are
yes.
running short of time. So kindly allow us to move forward with the next.
Thank you. Thank you. Thank you, sir. So here we are wind up our session. One next session will be starting very soon by Proshit. I think so. Thank you.
Thank you everyone for joining the session. Our next session will start within few minutes. Till the feedback form which you have given, please fill it as soon as possible. Now we will start our next talk on the topic application of machine learning in renewable energy, electric vehicle technology by Professor Prasenjit De. But before that, I am honored to read a short biography of Professor Prasenjit De. Dr. Professor Prasenjit De received his BTech degree in Computer Science and Engineering from the West Bengal University of Technology, Kolkata in 2010. An MTech degree in Computer Science and Engineering from National Institute of Technology, Durgapur in 2012. He received his PhD degree in Computer Science and Engineering from National Institute of Technology, Durgapur in 2018. He was an associate innovator with Niveo Technology, Gurgaon in 2012 and hardware graphic designer at Intel from 2017 to 2018. Currently, he is working as an assistant professor in the Department of Computer Science and Engineering, National Institute of Technology, Rourkela.